We will begin shortly.
Whether or not there's any other benefit, right?
Testing, testing.
Okay, I was always taught that well-typed programs don't get stuck, and that's good. But we're here to learn new things. So we're going to find out why you want your program to get stuck.
Indeed. So welcome to the talk with the scary title, Stuck Macros, Deterministically Interleaving Macro Expansion and Type Checking. And already from the first word, indeed, stuck. Ugh, that doesn't sound like a whole lot of fun. Why do we want our macros to get stuck? And the reason is we don't. What we're really interested in is something called type-aware macros, which I will explain in a moment. But the naive way to implement type-aware macros has a problem. It's non-deterministic in a way that I will make more precise again in a moment. And if we allow the macros to get stuck in a particular way, it restores determinism. So that's the overall goal. I want to propose an alternative to something called type-aware macros that is more deterministic. The kind of determinism that I am interested in is called confluence, and there's an official mathematical definition of confluence, but here's a simpler, more intuitive version, which is good enough for my purposes. And here's an example that has nothing to do with computers. Suppose that I want to put both an apple and a banana inside of a basket. It seems like it shouldn't really matter whether I put the banana first or the apple first. In either of those orders, at the end, I have the same result, a basket with both an apple and a banana. And so the property I'm interested in is when I am faced with this choice, I have to choose in which order to do things, then it shouldn't matter. With all of the orders in which I can do that, I get the same result in the end. Here's an example in which we don't have confluence. So if instead of starting with an empty basket, I start with an empty table, and then I have the choice of either putting the fruits on the table first and then squishing them with the basket, then I end up with squished fruits. But that's fine. I'm not bothered by the squished fruits. What bothers me with this picture is that if I put the basket first and then the fruits are inside of the basket and they are not squished, I get a different number of squished fruits depending on the order in which I do those two actions. And so that's why it's not confluent and I'm unhappy. In that simplified domain of fruits, I can already give you a flavor of my proposed solution with stuck fruits. So a stuck fruit is a fruit which really, really wants to be put inside of a basket. They don't want to be put on a table. And so if I try the wrong order, if I try to take the fruit and to put it on the table first, the fruit will say, no, you can't take me in. There's no basket on the table. And so I am forced to use the other order in which I put the basket first and then the fruits. And there's only one ordering, and so all of the orderings lead to the same result. So that's overview of my technique. For the rest of the talk, we will not be talking about fruits. I will spend the rest of the talk explaining this slide, which but this slide has the same shape as the previous one. We start with a small program, and there's a problem with this program, which is that it's not clear what its meaning is because the compiler has a choice, which shouldn't matter in which order it expands the two macros, $p2 and $p1. And if it chooses one order, we end up with one result. And if we expand it in the other order, we get a different result. That's bad because the programmer doesn't know what their programmer means. The programmer does not know what their program means, and the solution is to make some of those macros stuck so that there's only one path. And so there's only one needing. All right. So to explain this slide, I'll explain each part. The first of which, I keep telling you that we want type-aware macros, but what even are type-aware macros? That's the part where I explain that. So here's an example of a type-aware macro in a fictitious language that looks a lot like Haskell, but that we imagine is extended with type-aware macros. But before I tell you what makes this macro special, in which way is it aware of the types, it is a macro. And so, like on macros, it allows us to generate code so that we don't have to type it ourselves. And so what kind of code is this particular macro generating? It's generating functions like ID or traverse of ID or traverse of traverse of ID or traverse of traverse of traverse of traverse of ID. It's generating this family of functions. And what all of those functions have in common, and the reason why I call it macro pool maybe, is because they take a maybe that is nested inside of a number of, in this case, list, but it could be any traversable functor, and the traverse calls pull the maybe out to the outside. So, according to Simon Peter-Jones, all presentations must have this part in the presentation where we say, what's the one thing we need you to remember from this presentation? So here's that slide. Remember that if you're faced with this situation in which you have an applicative or a monad such as maybe, and you want to pull it out from many containers such as lists, you can do so. If you have n layers, you can do so by calling traverse n times with ID at the end. And the reason why I say that this is the one thing you should remember is not because it's the most important thing for stock macros. On the opposite, it's because you're probably not going to be using a language that has either type-aware macros nor stock macros, and so this is the most useful thing in your day life that you'll get from this presentation. So if you didn't know this trick, here's a trick that has a chance of being useful, because while the languages that you use day-to-day probably don't have type-aware macros nor stock macros, they probably have traverse and ID and traversable functors, because we're a functional programming conference. All right, so I was saying that this macro generates these kinds of functions, and so I would not write these functions by hand. I would write $pull maybe, and the compiler would call the macro would generate the code, and we would have one of those three functions. But wait a moment. How does the compiler know which of those three functions to generate? Because those three call sites look identical. And that's where type-aware macros differ from more standard macros, where it would receive as input, say, a number or something, telling the macro what kind of code to generate. It's just some pure function from that input, the integer, to the code. In this case, it's not the case. We don't need to give this input because the type-aware macro can look at the type of the place where we call it in order to figure out what kind of code that has this type it should generate. So the way in which the type-aware macro does that is that we extend the, in this case, since I'm using the template Haskell-like syntax, the macro runs in the QMonad, and so I postulate the existence of an action which runs in the QMonad, which returns a value of type. And so type is just some data type that has a constructor for every type in the language. And in this case, I'm only interested in arrow and maybe. But there would be plenty more. So get expected type returns a value of type, and then I can pattern match on it to determine which code I want to generate. And so since in this case, I'm generating traverse of ID, I just want to know after how many calls to traverse is it enough? When is the base case? When should I stop and generate ID? And in the types we have seen, it's always a maybe that is nested inside of 0 or more lists or some other functor. And so when we have reached maybe that is wrapped by 0 functors, then we know we're done, we've reached the base case. And that's why I'm pattern matching, and I'm seeing that, oh, if the function that I need to generate must have type arrow from maybe something to something, then that means I'm done. I should generate identity. Otherwise, I should recur. And so when I look at those three types at the three call sites of $cool maybe, only the first of the three call sites has a type that has the correct shape. It's a function from maybe something to something, whereas the other two call sites are functions from a list of something to something. They do not match. And so that's why the first call site gets expanded to ID, but the other two call sites get expanded to traverse of a recursive call. And now that we've expanded some code, so far there was nothing in the system that forced us to generate code that has the right type. And so after we're splicing in this arbitrary code, we need to switch to type checking, just to make sure that the code we've generated makes sense in that position. And in the process of doing so, either we learn that there's a type error, or we can learn some more information about the type of those recursive positions that I've just generated. And then the process can continue. Notice that for the second call site, which is now the first call site because there's only two left, it used to be a function from a list of maybe A to a maybe list of A, but now the recursive position has a smaller type from maybe A to maybe A, and that is how we have a chance to eventually reach the base case. But it's not guaranteed that we'll reach it. Maybe the macro will run forever at compile time. So I've just used the macro expansion to expand the macro into some code, and then I did some type checking in order to figure out the type of those recursive positions, and I'll keep interleaving between those two things until I have type checked all of the code, including all of the generated code, and until I have expanded all of the macros. And I can't do all of the macro expansions first because I need to know the types of those call sites in order to have a value that is returned by getExpectedType, and I can't do so that's it. I can't do all of the expansion first and then the type checking, and I can't do all of the type checking first and then the macro expansion, because I can only type check code if I have the code, and so I need to know what are the terms that are generated by the macros in order to type check that code that is generated. So that's why I need to interleave between them. All right. So now we have understood a bit more about this one slide I'll keep returning to, namely that what is happening is, as I said before, we start with an expression that has two macros. $p1 and $p2 are both calls to the pull maybe macro that I've shown previously. We'll use the same type aware macro during the entire presentation. I've just renamed the two call sites to P1 and P2 so I can distinguish the two. And it turns out that if we choose to expand one of the two occurrences first or the other, we get a different result at the end, which we don't want. So now that we've seen the mechanism through which type-aware macros compute their output, the next section, partial types, is the one in which we'll see how come we get different results depending on the order. But first, a message from our sponsor, Hackett. So Hackett is not really a sponsor. It's just that, as I said earlier, there are very few languages that actually support type-aware macros or stack macros. And so throughout the presentation, I'll insert those ads about those few languages so that if I've successfully convinced you that either type-aware macros or stack macros are cool and you want to learn more about them, I'm telling you about those few languages that you can try out if you want to learn more. So Hackett is one of them. The original one, its main feature is that it supports type-aware macros. It's its reason for existing. It's a language that was developed by Gélineau, and here are some other features in addition to type-aware macros which Hackett has that may make you want to consider examining the language more. So Hackett, the name comes from a mix of Haskell and Racket, and so the Haskell part is that the semantics of the language is very similar to Haskell. It's just that its syntax has a whole lot more parentheses. And that's an advantage for a language in which macros are used more often because it's easier for code which manipulates code to manipulate code that has a very regular structure such as what you get with S expressions, versus what you get with the giant, very complicated AST of Haskell expressions. So that's one aspect of Hackett. So the Haskell part, the Hackett part is that Hackett is implemented in Hackett, which is a language for creating other programming languages, and which gives a lot of benefits to those languages implemented inside of Hackett. For example, here's Dr. Hackett, an IDE, both for Hackett and for languages implemented with Hackett. And so it would be difficult to create an IDE for a brand new language, but since Hackett is implemented in Hackett with relatively low effort, they get to integrate with Dr. Hackett and to have these features that if you put your mouse cursor over an identifier, you can see all of the other occurrences of that identifier and where it's bound and even the type of the identifier, even though Hackett itself is a dynamically typed language. Anyway, so that was about Hackett. If you want to know more about it, you can check it out on GitHub. You can also search in its issue tracker for my original proposal about stack macros. But for now, let's go back to partial types. So, what are partial types? So, this is our original expression where we have two macro call sites, $p1 and $p2. And like I said, in order to expand them, we need to know the type of those two positions. So let's try to figure out what those types are. And I want to emphasize that we're not looking at the definition of pool maybe in order to figure out what is the type of pool maybe. We are looking at the code around the call site in order to figure out their type. So it's as if I had put an underscore, a type hole at those positions. I don't know anything about pool maybe. I'm inferring what its type should be from iterate, IDMay, and function composition, from the fact that $p1 and $p2 occur in a function composition. I know that the two positions, $p1 and $p2, must be functions. From the type of IDMay, just some function that's defined elsewhere in the program of type maybe A, arrow maybe A. I learn something about the input of $p2, since IDMay returns a maybe something. I know that $p2 receives a maybe something. And similarly, since IDMay receives a maybe something, we know that $p1 must produce a maybe something. And that's all we know so far. The type of iterate doesn't really tell us much more information. This is all the information we have, and unfortunately, it's not enough, because we don't have a concrete type for either $p1 nor $p2. We have this partial type that still has those question marks inside it. And those question marks are the unification variables that you create with the fresh action, if you remember this morning's presentation by Kini. All right, so we have this incomplete information that cannot be represented using the data type that I've introduced before, because we have those question marks. Instead, what we have is a value in a very similar data type, which has an extra constructor for the question marks that I'll call unknown. And that's a problem, because we, the compiler, we have this information of type partial type, but we are trying to give this information to the macro, which expects a value of type. And so what should we do? Which information should we send the macro? I'll give you a moment to think about how you will solve this problem. So hopefully, you thought that the obvious way to solve this problem is the obvious naive way, which I claim is wrong, but what I think is the obvious way to solve this problem, if we have too much information than what the macro expects, is let's change the system, let's change the type of getExpectedType to give the macro all of the information we currently have. Let the macro writers deal with it. So this has a benefit. Since we tell the macro all of the information we have, including the fact that we don't yet know the information at a particular position inside the type, it allows the macros to be smart. and to either give a nicer error message to the user if they know exactly where it is that the user needs to put the type annotation in order to solve this type error, or perhaps the macro knows that they can get the information from somewhere else. In this example, we're looking at the input type of the arrow. We're looking if it's a maybe something, but maybe in one particular macro, maybe they can get, maybe if it's an identity-like function, then they can look either at the input type or the output type, and they should be the same, and so they can get their information from either side. The macro has the opportunity to be smart about what to do if we don't have enough information for them. But they also have the opportunity to be dumb. And so our pull macro, our pull maybe implementation was dumb. It did not take into account the existence of the unknown constructor, because we thought it was returning a type, not a partial type. And so what it does is it pattern matches against the values we're giving, and if it doesn't match, it falls through and returns traverse of something. And so if we look at the $P2 call site, we're pattern matching on arrow of maybe unknown to unknown using the pattern arrow of maybe underscore to underscore, and that successfully matches. And so that's why $P2 expands to ID. Whereas with $P1, we're trying to match on arrow unknown to maybe unknown, and this does not match maybe underscore, because unknown and maybe are different constructors, and therefore we fall through to the second case and expand to traverse for $P1. And so now we can understand the first two arrows of the slide we'll keep going back to. We can see that $P2 expands to ID, whereas $P1 expands to traverse, for the reason I just explained, because we know that the type of $P2 is maybe something, but we don't know whether the type of $P1 is maybe something. We have a question mark. All right. So we've just done some macro expansion. What do we do next? We do some type checking. So now that we have expanded $P2 to identity, we can do some type checking in order to learn more information than we had before about the type of the call site of $P1. So before, at the top, we only had question mark as the information for the input type of $P1. But now that we have identity instead of $P2, we have more information. Now we know that it's maybe question mark to something else. How do we know that? Well, we know that ID may returns maybe something, and identity receives a maybe something, and therefore returns also maybe something. And now that the type of iterate comes into play, it's a function. It's a higher order function from a function of type A to A. So the output type of this whole function composition is the same as the input type of this whole function composition. And so since identity returned maybe something, the whole function composition returns maybe something, and therefore the whole function composition receives a maybe something, and therefore $P1 receives maybe something as well. So that's how we know now that we have identity, that $P1 receives a maybe something, whereas the information from ID may was not able to propagate through the $P2 call site before we knew that it was identity. And so that's why we knew nothing before. So now that we know that the type of $P1 is maybe something to something, now it expands to identity, because that's the logic for pull maybe. If it's maybe something to something, it's identity, otherwise it's traverse. And so this time $P1 expands to identity, but previously it expanded to traverse when we chose to expand $P1 first. And that's why when we follow the two different paths, we expand $P1 and $P2 in two different orders, that's why we get two different results. It's because of these partial types that the macro makes the stupid decisions early if we try to expand it when we don't yet have enough information. All right, so that's the problem. How do we fix that problem? Using stuck macros. So I will explain what stuck macros are after this message from our sponsor. So Typer is the other message, the other programming language which has a chance of supporting type-aware macros at some point in the future. It's not yet the case, but it's developed by Stéphane Monnier from Université de Montréal and I'm in Montreal as well, and so we talked, and I convinced him to implement not type-aware macros, but stack macros. So it's even more exciting than Hackett, perhaps, because it has stack macros, which I hope to convince you are better, but it doesn't have it yet. So that's a downside. But here are some other features which Typer does have. Just to let you know if that's a language you might be interested in trying at some point. So this slide looks a lot like the previous slide about Hackett, but it means the complete opposite. It does not mean that it's like an ML syntax, but with parentheses. On the contrary, it has ML-like syntax, but there is a straightforward process to desugar any ML-like expression into a syntax with parentheses. So in this case, the if then else is not a built-in from the language, which the parser knows how to expand into the equivalent syntax with parentheses, but rather the user can define their own identifiers and they will get desugared in a very straightforward way, which I'm not explaining here. I'm just telling you about the features in case you find it cool. Here's another feature which Typer doesn't have. So in most languages which have macros, those macros are introduced using a special form called define macro. And this special form takes in, well, the definition of the macro, but also the identifier identifying the macro, in this case, infix replicate. And then in the rest of the code that comes afterward, the macro expander knows whenever it encounters this identifier, infix replicate, I know this is a macro because I've seen it defined by define macro earlier. I know that I need to expand this at compile time, not at runtime. So Typer does not have this. Instead of a define macro, there is a regular function called macro with a lowercase m, which takes as input a function from syntax to syntax. And this function is transformed by macro with a lowercase m into a value of type macro with an uppercase m, which is a regular value. It's just in some opaque type macro. And we can use function composition or whatever to construct other functions which take in values of type macro or produce values of type macro. And there's nothing special there. What is special is how does the system know when to expand those macros, since there was not a defined macro special form saying that infix replicate is a special word. How does it know that this identifier needs to be expanded at compile time? Well, it's not the identifier which is special. When it sees infix replicate, fine, it's a function from int to a macro that will probably be expanded, be evaluated in the future, probably at runtime. But then it sees infix replicate of 3. Now we've applied the function of type int arrow macro to an int. So now this has type macro. So it's not the identifier which is special, it's the type. And so infix replicate 3, this has type macro, it does not have a function type. And so applying it to underscore star underscore, that won't work because it's not a function type, but it has type macro. And so that's what tells the system that this needs to be expanded at compile time. So that's another cool part. If you're interested to learning more, you can learn more on GitLab. But now, let's go back to our regularly scheduled stuck macros. I can at last tell you about my trick. So, one moment. Okay, so I think it's clear that the place where we went wrong was where we did not have enough information to determine whether the type of $p1 was going to be maybe something, arrow something, or if it was going to be list of something, arrow something, or int arrow something, because we had an unknown there. We did not have enough information. And yet we allowed the macro to be dumb and to make the wrong decision. We allowed it to look at this and decide, nah, it doesn't look enough like a maybe something. It's going to fall true to the second case and expand to traverse. So we should not allow the macro to do that. And the way in which I propose to prevent the macro from doing that is to go back on this decision that I said was the obvious naive way to do it. Let's go back to this world in which getExpectedType was returning a type rather than a partial type. It's the API we wanted at the beginning anyway. It's the more intuitive API. But what are we going to do with those unknowns? I cannot give a value of type unknown as a result of get expected type to the macro, because what do I do with those unknown constructors? I cannot encode them in the type. But hey, we're in Haskell, so I don't need to pick a value. I can use bottom. But my colleagues might frown on me for doing that, but it's technically allowed in the language. So I can convert my partial type value into a value of type using those bottoms. And then what happens in Haskell when you try to force a bottom is it throws an exception. So what I want for those stock macros is a slightly different semantic, but let's look at the familiar part of the semantic first. Here, for $p2, when we are pattern matching on an arrow of maybe bottom to bottom, using the pattern arrow of maybe underscore to underscore, this does not force any of the bottoms, so nothing special happens, no exception gets thrown, nor does the special semantic that I'm hinting at happen either. So the pattern match succeeds and we produce identity. So that's what happens for $p2. But for $p1, something else happens. We are trying to pattern match on the bottom using maybe underscore. How can we figure out whether bottom is the same as maybe underscore? Well, we need to force the bottom, which would normally throw an exception. But for the special case of those stock macros, I propose a different behavior. Instead of throwing an exception, we should write down the fact that pull maybe is interested in the value of this particular question mark and keep track of that fact so that if later on we learn more about this unification variable, we can know that it is now safe to go back and evaluate the rest of pull maybe. So the computation is suspended. It is temporarily stuck, hence the name. And while it is stuck, we can do something else. So what this means in the context of this slide is that there used to be two paths. One of those two paths was stupid because we did not have enough information to expand $p1. We should not let it make the dumb decision of deciding that question mark is not enough, like maybe, that it should expand to traverse. And so we only have the paths which are controllable, but there's only one path, so all of the paths lead to the same answer. And that's my solution. Just don't do the dumb things, wait until you have enough information. So by expanding $p2 first, since we're interleaving micro-expansion type checking, we get more information about the type of $p1. And so after doing that, $p1 is no longer stuck. And so after expanding $p2, we can expand $p1. And that's how we get the final answer, which is the correct answer that we want to expand $p1 and $p2 to identity in both cases. And that's my talk. Yes?
So those are questions for us to ask you or for you to ask us?
It's a menu of recommended questions. If you don't know what to ask, I have some bonus slides for them, but I will allow questions that are off the menu.
So, the implementation of this.
No. During the unconference, David Christensen and I worked on a prototype macro expander that is structured in such a way that we can implement stock macros, but I have not yet implemented stock macros, and neither has Hackett nor Typer. This is a proposal that I made separately to both language authors, and there was no progress, so I'm making a more public proposal.
Sweet, that's awesome.
So hopefully there will be an implementation at some point. If not by them, then by David Christensen and I. Thanks.
Two things. One, talk to me about propagators. Two, at the end, when you get done with your type checking, you've inferred as much as you can through the type checking process, and you have all stuck macros still, sometimes. What do you have to unstick in the case where you didn't actually, you grounded everything that was going to happen through your entire type checking process, and you're still stuck. You haven't determined whether or not this argument should be a arrow from maybe. You're missing a step there for like a finalizer, like, you know, ground me out anyways into one of these cases kind of thing, or something. It seems something like that to me, at least.
It sounds like you're asking one of the questions from the menu. What?
When they get stuck on each other? Well, it's not
Yeah.
actually if they get stuck on each other. It's like if I can do that, I can get into this stuck in this thing with no players in the game other than me.
F equals $P1.
Yeah,
Right?
yeah,
So if you write an expression such as this one or such as f equals $P1 in which there is not enough type information for the macro to make a decision, then you don't have enough information. It's a type ambiguity
so-
error. And do you have a follow-up question, or should I?
it was more like, so there's no like show.read kind of defaulting going on to ground out at the end, even if you if it's just because there was no choice being made. Okay, that was the piece I was looking for.
It doesn't like automatically generalize with Hindley-Milner if there's no constraints.
Okay.
You have to know enough information to get the macro unstuck.
Cool. Yeah.
Perhaps. If we had an implementation, we could try it out.
I guess like it gives you the answer you would do by hand, right? So this answer has no answer even if you did it by hand. But the other one has a clear answer you could figure out on your own as a human being, right? So like in this case, there's no answer no matter what. But in the first case, there's a clear solution that you want to get to.
Which first case and which second
The
case?
case in the slides.
In the case in the slides, there
Yeah.
is a solution and the system can find it. In this case, I would argue that there is still a solution, but the system cannot find it.
Oh.
Which, if do I have time for the next few slides which explain that?
Yeah, and I'm going to ask you the other question that you have up there as
Oh,
well.
great.
I'm guessing that you can definitely construct something non-confluent because the macros you can do anything. I want to know if you can detect the non-confluence, or you think that we shouldn't bother detecting it. You can help. Maybe I'm wrong and you can't.
The intent is to restrict the system so that you cannot write a set of macros that are not confluent, but this depends on the macros being pure functions. If you use template Haskell where you can use IO, then it's already not confluent, and so giving them access to the type of the positions where they need to generate the code does not make it worse. But if you start with a system where your macros are pure functions and they do not have access to the types, then it's confluent. But introducing access to the types makes it non-confluent unless you make them stuck. But since I've started with those bonus slides, so here's an example in which it's unfortunate that this example gets stuck and that we have to fail with the type ambiguity error. Because even though on the face of it, it looks like we don't have enough information, that all we know is that they are functions because they're part of a function composition, actually, pool maybe, it generates a family of functions, and all of those functions produce a maybe at the end. And so we ought to be able to know this information in order to get the system unstuck. Because if we know that $P1 and $P2 both return a maybe something, then when we propagate this information, oh, $P1 returns a maybe something, and for $P2 receives a maybe something as well, and because the output of the argument to iterate is also the input of the argument of iterate, then $P1 takes a maybe something as well. And so, yeah, we really wish that this example was going to work, and so how can we fix it? This has nothing to do with confluence, but it has to do, I think, with API design. So I think that with the API I've suggested so far, with get expected type, it's too easy for the programmers to write selfish macros which ask for information but never give anything out in return. And I think it's very likely that the programmer will write that because they're concerned about the task of writing their current macro. They want to know the current type in order to pattern match on it and to figure out what to generate. And so I'm sure they will find the documentation for get expected type, but probably not the documentation for the other function right next to it in bold letters. Please call this set partial type, in which the programmer may choose to generously give out some information to the system in order to help out with type inference. So what I am proposing is a different API where instead of having two separate functions, set partial type and get expected type, there would be a single operation set partial type, and that is the way in which you will bind variables representing types that you will then pattern match on. And so since I know that the programmer is going to look through enough of the documentation to be able to get their type, if the only way in which they can get their type is through the function that gives the type information, then the programmer is likely to read the documentation for that function that explains that, yeah, give as much type information as you know at this point of your program because it will help type inference. You said you wanted to ask the second question, or did I already answer that? Out of time?
Is there anyone else with a question, or let's thank the speaker? And,
Thank you.